In this video, we are going to learn how to graph polar equations by plotting points. And in this lesson, we're going to look at the graphs of cardioids and limaçons. So, in order to graph each of these equations, we're actually going to first check for what symmetry it might have. And that can help us pick what angles would best help us find the shape of the graph. So first, I'm going to test this for symmetry. The first test is going to be for symmetry with the polar axis by plugging in negative theta. So r is equal to 2 minus 2 times sine of negative theta. But the negative can be taken out because sine's an odd function. Give me 2 plus 2 sine theta, which is not an equivalent equation. So it might not be symmetric with the polar axis. But now let's check for symmetry with the line theta is equal to pi over 2, which we do by replacing theta with pi minus theta. So if r is equal to 2 minus 2 times sine of pi minus theta, which I could rewrite as the difference formula for sine. So r is equal to 2 minus 2 times sine of pi cosine of theta minus cosine of pi sine of theta. Which gives me r is equal to 2 minus 2 times sine of pi is 0 times cosine of theta minus cosine of pi, which is negative 1 times sine of theta. The minus and negative makes that a positive sine of theta. When I distributed that negative 2, it gives me a negative 2 sine theta. And this first term just goes to 0. So I end up getting r is equal to 2 minus 2 sine of theta, which already tells me that this graph is symmetric about the line theta is equal to pi over 2. With respect to the line theta is equal to pi over 2. Checking the other ones, I could try negative r to see if it's symmetric about the pole. 2 minus sine of theta. When I divide by a negative, r is equal to negative 2 plus sine of theta, which is not equivalent. And I can also check for theta plus pi for the symmetry as well, for that symmetry about the pole, which would be 2 minus sine of theta plus pi. Give me r is equal to 2 minus 2 times it. I left out a number there. 2 times the sum formula, which would be sine of theta cosine of pi plus cosine of theta sine of pi. Sine of pi is 0, so that term goes away. Cosine of pi is negative 1, making this a negative sine of theta. So this simplifies to 2 plus 2 sine of theta, which is not equivalent. So it may not be symmetric about those, but we do know one of the symmetries is about the line pi over 2. So if I find angles from the fourth quadrant to the top of the first quadrant, then I should be able to reflect all those points across the line and get the full graph. So I'm going to plot points between negative pi over 2, the very bottom angle, and pi over 2, the very top angle, and that'll reflect all my points to get the full graph. I'm going to put 0 in between them, and I'm going to plot negative pi over 3, negative pi over 6, pi over 6, and pi over 3, which are all unit circle values. Start with negative pi over 2. Sine is negative 1 down here, so I get 2 minus 2 times negative 1, so that's 2 plus 2. Give me 4. Sine of negative pi over 3 is negative square root 3 over 2, which when I plug it into here, gives me 2 plus the square root of 3, which I'm going to use my calculator here. 2 plus the, 2 plus the square root of 3, which is 3.73. And for negative pi over 6, I would get negative 1/2. So 2 minus 2 times negative 1/2 makes it 2 plus 1, which is 3. And then sine of 0 is 0, so it's 2 minus 2 times 0, which is just 2. And again, I can also find these same values just by plugging this into the calculator, keep my calculator in radian mode as I do so. I can also do 2 minus 2 times sine of pi over 6, which is 1. 2 minus 2 times sine of pi over 3, which would be 0.27. And then 2 minus 2 times pi times sine of pi over 2, which would be 0. And then I will plot all of those points. So negative pi over 2, 4. So 1, 2, 3, 4. Negative pi over 3, which would be this one, would be 3.73, so about right here. Then negative pi over 6 would be 3, so right here. 0, which would be there, would be 2. Pi over 6, which is right here, would be 1. Pi over 3 would be 0.27, so very close to the pole, and then at 2 it would be at the pole. Now all these points are reflected across that line. Pi theta is equal to pi over 2. So I get another point here. This point reflects across over here. That point reflects across to here. This point reflects across to here. That point reflects across to here. And now we have all of our points and we can graph. So this is referred to as a cardioid. Kind of makes a little like heart shape as you go through, hence the name cardioid. Because that's this little divot up top making a little heart. Sometimes people call it an apple too. So cardioids have this form where you have a plus or minus a sine or cosine of theta, where both those coefficients are the same. Now let's look at when they're not the same and what type of shapes we get. So let's look at r is equal to 3 plus 2 cosine of theta. We'll test for symmetry. R is equal to 3 plus 2 times cosine of negative theta, which I can get rid of the negative on the inside to give me 3 plus 2 cosine of theta, which is the same equivalent function. So we say this is symmetric with respect to the polar axis. So about this line here, which can go straight across as well. Now I'm going to test for symmetry to the line. Theta is equal to pi over 2. That gives me r is equal to 3 plus 2 times cosine of pi minus theta to check for this one. So r is equal to 3 plus 2 times the difference formula for cosine. So cosine pi, cosine theta, plus sine pi, sine theta. Sine of pi is 0. Cosine of pi is -1, so this is negative cosine. That gives me 3 minus 2 cosine of theta, so it's not symmetric about that line. And most of the time when it's not true for both of these, it's not going to be symmetric about the origin. But this is enough information to get us started. So the polar axis means it's going to reflect across here. So I'm going to pick angles between 0 and pi to make this one work out. And right in the middle is pi over 2. And then I'll use pi over 6, pi over 3, and then 2 pi over 3, and 5 pi over 6 to get enough angles to graph this. So first plug it in 0. Cosine of 0 is 1. So I'll get 3 plus 2, which is 5. And then cosine of pi over 6 is square root 3 over 2, which when I multiply by 2 will give me just the square root of 3. So I have 3 plus the square root of 3, which should be 4.73. Cosine of pi over 3 is 1/2, so this becomes 3 plus 1, which is 4. Cosine of pi over 2 is 0, so this becomes 3 plus 0, which is 3. And then cosine of 2 pi over 3 is negative 1/2, so it's 3 minus 1, which is 2. And then cosine of 5 pi over 6 is negative square root 3 over 2, so this will be 3 minus the square root of 3, which is 1.27. And then cosine of pi is negative 1, so 3 minus 2, which is 1. Now I'll plot these points. So 0, 5, 1, 2, 3, 4, 5. Pi over 6, which is 2 tick marks up, is at 4.73. So that's 5. So 4.73 would be about right there. Pi over 3 is 4. Pi over 2, which is straight up, is a radius of 3. So 1, 2, 3. And then 2 pi over 3 has a radius of 2, so the next 2 tick marks over. 1, 2. 5 pi over 6 is 1.27. So 2 more tick marks over. Pretty close to 1, and then 1. And then all these points reflect across that polar axis. So this point reflects down to here. That point reflects here. This point would that reflects here. That was the incorrect placement. Put it on the wrong tick mark. See if I can cover up that point. Some white out. There we go. This point reflects down here to 3. This point reflects down here to 4. That point reflects over here. 4.73, and now you'll see here we don't get a actual cardioid where it's like a nice bend right there. It starts to come in, but then it comes right back out. And this is what we call a limaçon. It's a French word for a snail or a spiral staircase. But there's 2 situations for a limaçon. Either the B value is less than the A value, which is what we have right here. A is greater than B. Or A is less than B is the other situation for a limaçon. And let's see what happens with that one. So this one is going to have a very similar symmetry since it's just that cosine function. So it's going to be symmetric with respect to the polar axis again. And we can check that. So r is equal to 1 plus 2 cosine of negative theta, which that being an even function makes this 1 plus 2 cosine of theta. You can get rid of the negative. So it is definitely symmetric with respect to the polar axis. But if I check the other symmetry, it probably won't work either. It's a very similar form, but we'll double check just to be safe. So 1 plus 2 cosine of pi minus theta. We'll use that difference formula. So r is equal to 1 plus 2 times cosine of pi, cosine of theta, plus sine of pi, sine of theta. Sine of pi is 0, so that term goes away. Cosine of pi is negative 1. Which leaves me with r is equal to 1 minus 2 cosine of theta, since cosine of pi is negative 1. So minus 2 cosine of theta, which isn't the same. So it's definitely not symmetric with respect to that line. So we're going to use actually the same exact angle points because that symmetry is the same. And we'll see what happens when we change that value for A, like the 3, to a 1 and make it less than the other one. So 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then pi. And we'll see what happens here. When we plug in 0, cosine of 0 is 1, so 1 plus 2 is 3. And then we have cosine of pi over 6 was a square root 3 over 2, which gives me 1 plus the square root of 3. which would be 1 plus the square root of 3, not line 3, 2.73. And then cosine of pi over 3 is 1/2, so that's 1 plus 1, which is 2. Then you have cosine of 1/2, which is 0, so that gives me 1. And then cosine of 2 pi over 3 would be negative 1/2, so that comes 1 minus 1, which is 0. Then cosine of 5 pi over 6 is negative square root of 3, so 1 minus the square root of 3. We actually get a negative radius, and I'll show you what happens with that when we go to graph it. So that's negative 0.73, and cosine of pi is negative 1, so 1 minus 1 is negative 1. So as I go to graph, starting with 0, which is all the way on the right, we have a radius of 3, so 1, 2, 3. Then at pi over 6, we have a radius of 2.73, so a little bit inside of it. Pi over 3, we have a radius of 2. At pi over 2, we have a radius of 1. Then at 2 pi over 3, it is 0. So it means we have reached the pole when we start to curve in here. But that 5 pi over 6 is now a negative radius. So instead of going this way along your radius, it actually goes the opposite direction. So along this axis here, it goes to negative 0.73, which is just inside that circle. Then at pi, it's a negative radius, so it wouldn't go left, it would actually go right to this 1. And now all these points reflect. So this point reflects down here. That point reflects over here to 2. This one reflects to 1. And this point reflects over here. And you still have your point at your pole and everything. So as I graph this, what actually happens with the graph is the first go around, it curves around, goes through the pole, and actually makes an inner loop, then comes back around. So there's two different types of limaçons, ones that have no inner loop and ones that do have an inner loop. So you have, if A is bigger than B, it is without an inner loop. But when A is less than B, it is with an inner loop. And that is how you graph polar equations by plotting points.